Welcome to my video on Introduction to ATE Design. This video is created to give you a sort of a high-level overview of what an ATE is and how you should approach building one. So let's get started. So what is an ATE? If you've found this video, you're probably familiar somewhat with what an ATE is and what it does, but ATE just stands for Automated Test Equipment. And this is just an integrated collection of instruments, software, and hardware used to test a device. There's a lot of complicated devices, especially embedded devices, cell phones, radios, set-top boxes that are too complicated to do efficiently on top of a benchtop test. So if you want to verify the functionality for it, then you need some sort of automated test equipment to do it. It's also used in bigger shops for what they call smoke racks, or for if you're using a Jenkins pipeline to do automated testing of builds. That's very, very valuable as well and can be used in that application. The problem with ATEs is they can be very expensive if you approach the problem wrong. Instruments are expensive. Integrating them together to act together is expensive. It's kind of like you're hiring a bunch of A-list actors and trying to get them to play nice. Sometimes they don't, and you need to find that out quickly. But if you can bring them up and get them deployed, they will pay for themselves very quickly. And the reason for this is that your per unit test cost goes way down. An example of this is you may have a benchtop test that could take 4 to 8 hours for a technician to verify the functionality on. And in a lot of cases, you can do that automatically in 5 to 10 minutes. And that 5 to 10 minutes can be unattended time, which is a huge selling point, is you could have one test technician or one operator loading up one or more test systems and going and doing something else while they test. It also allows for long-term automated tests where you have something testing continuously for days or months at a time. That's not where you don't have an operator having to sit there and watch it. They're pretty much a game changer if you haven't used them before. They're quite a bit of a step up from what you've done in the past, or a lot of places have done in the past if you're not used to them. And they don't have to be that hard, but they usually are. They usually are in a lot of cases. So why do you need an ATE? You need to ask yourself these questions. Do you want to dramatically reduce the cost of testing? Do you want to enable continuous design verification during development? And this is the case where instead of you're given a black box at the end of the development cycle and then you got to integrate it into production, that your design teams are continuously testing on the same test hardware that your manufacturing teams are going to be using it to verify at the factory, so that when you get to that handoff stage, there's no last minute gotchas of one side or the other not being compatible. It's you test it as you go through the design cycle and then you launch quickly. If you need to do any sort of hardware in the loop testing, then you're going to need an ATE. And if you're not familiar with hardware in the loop, that's basically you have a set of instruments inside a test rack that are simulating a device that your unit is trying to connect to. So for instance, you may have a flight computer, but you need to simulate the fuel sensor, or you may have a CAN controller that goes in an automobile that needs that's like an engine controller that needs to simulate. It needs to hook to a simulated engine in order to test it out properly. And in a lot of cases, it's the only way to interface to an embedded device, especially if you get like a flight computer or a subcomponent of a larger system that has a high pin count. The only way to effectively test it is that you need to hook it to some sort of automated equipment just to get to the different pins. So there's a couple different approaches to do it. Some people do the test system approach and some people do a test platform approach. There's pros and cons to both of them, but I want to go over them real quick. There is a difference. So in a test systems are typically they're specific to a particular product or product family. They're not general purpose typically. You have a product, you design a test system to test that product, and away you go. This is very common in like avionics and military projects, where the project is paying for a test development, and so they want a piece of hardware that's theirs and used for their equipment. It's not a good idea, but that's what they do. Test platforms, on the other hand, is on the other end of the spectrum. They're typically generic for a broad range of products, and this is what gets people into trouble, is you want to make it generic enough to test your set of products so that it can get most of the or all the functionality you need for the set of tests you need to do on your product lines. But you don't want to have a Swiss Army knife. If you get too generic, then you've basically just got a set of collection of random instruments that you have to reconfigure every time you want to use them. So typically in a test systems, the products connects directly to the test system, so that you end up with whatever interface that product used. That's usually you have the mirror of that on top of the test system, and that's what you get. And usually when on the system interface between the system and the product, there's no switch matrix or interconnects like that, and so it's pinned out specifically to the product that test system is designed for. This is in comparison with a test platform, where you typically put a switch matrix between your instruments and the unit under test, and then the product connects through what they call an interface test adapter, or ITA typically. You can also use cable harnesses for this, depending on how complex you want to do your ITA, but they can get a bit pricey depending on how much you have to adapt from the product connector to the test system switch matrix connector. This has a lot of advantages for you in that you can basically hook any product up to the test system's instruments, and then you change your switch paths so that the right instrument goes to the right pin on top of the product you're testing. Test systems, again, they typically have a rigid set of defined functionality, but they do that functionality well. So you spec out, I have a product X, it needs to do Y, the test station will test for Y, and it will do that all day long. And you can optimize that so your TAC rate for your test can go lower that way. Test platforms are typically flexible. You design a flexible set of predefined functionality. So instead of saying, product X needs a DMM measurement on channel 1, or to do an oscilloscope capture on channel 2, then what you say is that I have a DMM measurement test basically, and then I'll have parameters for that test that will define the switch path, which channel I want to switch in and out of, and will define the test parameters. And once you get those set up, then you don't have to do as much test development because all of the core test logic has already been done. But the problem with it is that you add the added complexity of having to make it more generic to suit multiple use cases. Test systems typically have a less initial cost, but higher long-term costs, and we'll get into the reasons for that. So if you're building a one-off tester for a small product line that's not going to be around for long, then sometimes it is more efficient just to go with a test system and put something together, run your tests, and then tear it down. But for long-term maintainability, you don't get some of the advantages you'll get with tests if you go with a test platform approach. Test platforms, typically you have higher initial costs because you have to spend more on your upfront design, but you have lower long-term costs, and this isn't just in hardware, so that you get, we'll go into more detail in a later slide. But plan on spending more to get the test platform up and running, and then you'll recoup some of that, or actually you'll recoup a lot more of that later on, but it will be over a longer time frame. So the other thing you need to be aware of, test systems typically are less complex to develop, and they're less complex, and they require a lot less skill to maintain. They take less skill to develop, but typically you end up with more maintenance issues down the road. Test platforms, I'm ahead of myself now. The other thing you need to be aware of is that there's typically with test systems, there is a lower risk of failure on them. You have a predefined set of tasks, and usually most test engineers don't have a problem getting to the end goal on top of a test system. Test platforms are a different animal. They're usually much more complex, and they require more skills to develop, a lot more skills to develop. It's not that bad once you understand the problem, but if you don't know what you're doing, then you will run into issues with it. And depending on how many people get involved, depending on if you fall into the design by committee traps, depending on how you structured your test development, you will have a high risk of failure with that. One of the problems with test platforms is people want to go for what they call big bang delivery. So you go through development cycle, and at the end you have this multi-purpose Swiss Army knife that will do everything to everybody. Never works that way. You need to divide it into smaller pieces of deliverables so that you have something, you're delivering something along the way that's valuable to the corporation. And sometimes you won't have your entire test platform spec'd out for years. It can take you years to get some of these things done, which doesn't mean you spend a couple years of development money and then start reaping the benefits. As you can get concrete benefits from a test platform approach from day one if you structure your delivery cycle correctly. So if you have the choice between test systems versus platforms, which ones should you go with? Which approach should you use? In pretty much all situations, you should use test platforms, but you should approach the problem correctly. And this is the simple reason why. This is the best way I've thought to describe it. But basically, any development group that can pull off automated test platforms will always beat their competition that can't. Automated test platforms take longer to get going, and it's not a one-off project type deal. It's like you'll be continually messing and developing on the platform for the life of the company, basically. But once you get ahead of that initial deployment and get into the learning curve effects, then you will leave your competition behind. You will do things that they just can't pull off. So let's talk about why test platforms fail. The first reason is a lack of understanding of what they really are and how they add value. And the second one is just poor design methodology. So the thing you need to understand is test platforms are not glorified test systems. They're not, super complicated test systems that have every bell and whistle under the sun. What they are is a collection of instruments, software, and hardware interfaces, of standardized hardware interfaces that you will be using to deploy tests to. They're not any individual implementation. This gets confused by a number of corporations and a number of people I've talked to is that your test platform isn't a specific tester. So it's not a specific test station. You may have an automated test equipment number one or whatever you want to call it. And that station is not your test platform. It is an implementation of your test platform. And in any given organization, your test platform may fill different station variants. So what is the components of a test platform then? So you're going to want to have a standardized set of instruments. And it can be a hard sell sometimes because you may have a project or a product line that are asking, well, why do you need a $5,000 DMM when my product only needs a $2,000 DMM to be tested with? And honestly, it doesn't matter how much your hardware costs. The cost of test and the cost of having a non-standardized toolkit is more than the cost of that instrument. And so what you want to do is you want to select which instrument capabilities you need as a company and then standardize on top of that. And this goes as a specific of, for instance, if you're putting a DMM in a Pixie crate and you put a DMM in slot 2 of your tester, you always put it in slot 2 of a tester. If you filled a tester variant that doesn't need a DMM, slot 2 is empty. You don't fill it with another card. Okay. The other thing you standardize is you have a standardized set of software libraries. You need to differentiate the library developers from the test developers. And you should never be running source code on top of it on a project by project basis. In the tool change I typically use NITestStand for this. And then there's two components to that. The test sequences, which is your set of test steps that you will be running, and the support libraries. And the support libraries are always built libraries. So if you have an engineer that needs to do a test and he needs to do a DMM measurement, he goes and uses the standard library. If the library does not support the testing he needs, you need a problem report, you need a bug request, you need whatever your company calls it, you need a change request, and then you have it may be that same engineer or it may be a different group, but you have somebody go in and they make the change in the library, they test the library, and then they deploy a new version of the library. That way, over time, your libraries get better and better because more people are using them, more people are finding bugs with them and fixing them. And then if one project adds a functionality to the library, then another project can use it further down the road. The other thing you do with this, as well as on the software library side, is typically you want to do a hardware extraction layer. And there's a couple ways to do this. I have another video that explains how to set these up. But in a lot of cases, what you want your test flows to be is a collection of what the steps are, but not necessarily the exact implementation of the instrument commands. So for instance, for a resistance measurement, you may need to measure resistance on channel 1 and return the result. But you don't care if it's an Agilent DMM or if it's a Keithley DMM, as long as both of them have the capability to do that. So the more you can keep it at that level, so you have a DMM instrument class, and in your test sequence, you just call the arch type or the parent class, and then you don't call the individual implementations of those instruments, then that minimizes your rework in the long run, because when instruments go obsolete, if you set things up correctly, then you just pull out the old instrument, put in the new instrument, change the constructors so that you're using a new type of DMM, and then the rest of your tests, your validated test logic should work. You'll still need to do validation on that code, but it should minimize the amount of churn you need to do on it. Another thing you want to do is try and standardize your set of mechanicals. This is an overlooked part of the process, depending on your company and your industry. I've seen it all over the place. Getting some management types to buy in on top of buying racks and ruggedizing your test systems is sometimes hard, especially as if you're working in a software world that isn't used to fielding something like this. But this is an important part of the test development. You need to spec out a series of vendors and a series of parts you use in your test systems. If you're using a specific brand of rack, I recommend Hammond Manufacturing's knockdown racks. They're easy to get, they're easy to store, and they've got a number of sizes I like. Then all the testers use the same set of racks. All the testers use the same type of rack shelves. They use the same type of power supplies or UPSs. They use the same type of power distribution units, and all that stuff has nothing to do with the test code per se, or it's external to that environment, but they're all important to keep them as standardized as possible, partially because then you can keep spare parts and replace things if they break, and partially that it allows you to keep them all consistent with each other. So, and then the other major one that gets overlooked sometimes is you need a standardized set of wiring and interfaces. You need to define how these things are wired. You need to define how you wire your labels inside the chassis and on top of the drawings. If you're using DB connectors to connect to the test station in the switch matrix, you need to keep using those. If you're using something like a Virginia panel or a Mac panel interface, then you should be using that. Whatever your way of connecting your units to the test systems is, you need to define it and try and keep it as standard as possible. So that's the components. So if that's what a test platform is, then how do they add value? And the key one we've just talked about was standardization. Once you get them all standardized and you basically have a standard set of building blocks you use to create test stations with, then you can take advantages of economies of scale. And this may get a little boring for you guys that don't like economics, but it fits really well to what's really going on with these ATEs. And once you've got the economies of scale, then you get some very interesting learning curve synergies. You get to go up the learning curve faster, and you get to do it more, or what's the best way to put it? You go through the learning cycles more iterations at a time. You also end up with better cost spreading. One of the things we'll talk about this more in a minute, but with a test station, basically the entire cost of the test station is baked into its development cycle. Whatever it costs you to put it up, the project writes a check for it, and that's what you get. And then the quality of that test station will be dictated by how much money you get and the strength of your engineers. when you do a test platform, the cost is spread across many test stations and many projects. And so the cost per test station is typically lower, and the quality of the test stations are typically higher. We talked about risk and the difference in risks between test stations and test platforms. And in the long run, you end up with a lot of risk reduction by doing a test platform approach versus using a test systems approach. And we'll get into that. And then the tricky one to talk about is the marginal cost of test development. This is the one of the killer features if you set your ATs up right, and if you manage it wrong, you will kill them. So, all right, we went over this a little bit. Standardization, you've got to standardize your instrument and test libraries at a minimum. And go with the mantra, don't reinvent the wheel on every project. Another way of putting this is, for the software guys, you may be familiar with the drive principle. Do not repeat yourself. If you write a DMM driver once, use it across the board. If it doesn't work for everybody, then figure out why and either write a different driver if necessary, or add the functionalities to the driver you've got until it works. As long as you spec things up initially correctly, then you should be fine. If not, you may have to swap out equipment. So economies of scale. Standardization does allow. The big thing with standardization is the economies of scale. So if you standardize, you have more copies of the instrument code being used in different ways. And if you're using it in different ways, you've got more people banging on the code, more people trying to break the code, more people finding bugs, more people fixing bugs. And eventually your code cries uncle, and it just works. You'll end up with a stable version that you won't have to change for years. So once you have enough critical mass of systems, then you get some learning curve advantages. Because one of the things that a lot of manager types don't realize, well, I think they know, but they don't want to admit it, is that each system has its own learning curve and quirks. It really does. If you bring up a new system, there's differences between it and other similar systems, and there's always things that go wrong that you have to solve in integration. So it has its own learning curve, its own quirks, and even with reuse, you basically reset this curve for each test system rollout. You have to create a new set of drawings. You have to create a new set of documentation for it. You have to do a new validation procedure to pull it out. It has to go through a new ECO process. And anything you learn on that typically stays with it in a test systems approach. So if product A has a test system and you find something interesting that could save the company money in test time or better test results, it's not necessarily applicable to the tester used on tester B. But if you standardize a test platform, then each test station is not starting from zero. So if you're on like variant 4 of your thing, you've got 3 other fielded test stations, or in some cases you may have 10 or 15 test stations per variant. And so you could have 40 or 50 test platforms or test stations out there already that people have been putting product through. People have been testing the interfaces. People have been testing the instruments. And so you're starting on a much higher portion of the learning curve than if you were just doing a one-off implementation. And then anything you learn on top of your test station, on top of your new product, can be done and then could be potentially rolled into other test stations. This is a good opportunity for getting some quick process improvement savings. The projects don't have to fund. Typically, projects don't want to fund process improvement on top of existing product lines. But if you end up getting, for instance, you have a new version of the product come out, and then during the product bring up, you refactor some code, and you come up with a more efficient measurement method that is, the code is done and validated on the new product, then you can have a better case to say, okay, look, this worked out fine on the new product line. Here's all our validation documentation, all of our data. It's close enough to what we need on the old product line that we can spin up a process improvement cycle and say, okay, look, for a fraction of the cost it took us to develop it, we can implement it on an existing product line and pick up some time savings or some cost savings somewhere. So for cost spreading, this goes a bunch of different ways. It depends on a lot of the problem with the cost spreading aspect of it too is that typically the buckets you use for development are different than the buckets that are used for ongoing maintenance. And so as a corporation, you'll end up being more cost efficient this way, but your individual departments may not necessarily be so. So the primary cost categories is you've got the initial NRE, so the non-recurring engineering costs. This is the setup costs and the cost to develop the station and build it initially. Then you've got the ongoing maintenance costs. And these are always underestimated. It's especially by a lot of organizations when they set up their incentives. The project is done when the system is delivered, but then the factory may run with that system for 20 or 30 years. And pretty quickly, the cost of the factory using the device will exceed the cost of the equipment itself. And this is because you're paying for the labor to use it and you're paying for any mistakes it misses. And one of the overlooked things in a lot of corporations is downtime costs. If this thing goes down and you've got factory workers sitting around not getting paid, in a lot of cases, the production supervisor will assign them other tasks, but then that's a cost to the corporation of if this thing goes down and it's down for any significant amount of time, then that is money being burned. But with standardization, you end up lowering your initial NRE, so you end up with more reuse. There's less to do. You don't have to build a DMM driver every time. You don't have to build a switch matrix interface. It's already done. You're picking and picking up what you've got and using it. You end up with lower maintenance costs. You have more systems, per spare. So if you've got a $50,000 piece of equipment for your test equipment, and you've got one in the test system and hopefully one on the rack, but I've seen a lot of places that won't justify the cost of leaving that amount of money on the shelf, then your spare cost per system is $50,000. If you've got 25 systems out there and they each got a $50,000 instrument in them, and then you've got one spare, then your spare cost per system is only $2,000. And in a lot of cases, you'll have enough excess capacity. You may not necessarily need a spare. You really should anyway, but you get the option that you can lower downtime by cannibalizing. And this goes two ways, because if you're standardized enough where your test platform can be used across product lines, then you can, if you have a system go down, in some cases, you can borrow parts, and in some cases, you borrow entire testers or test stations from other product lines. And the borrowing concept is very useful if you've got a high rate manufacturing run where you're trying to stuff the product line. So, for instance, the initial run for a set-top box maybe 5 or 10 times what your monthly run rate is, because you're trying to get enough units out the door and into customers' hands for the product launch. And so to meet schedule on the product launch, you need to be able to test 5 to 10 times, in some cases more than you would during your normal rate. So you can either build more systems and have them sit around, or you can make it a judgment call or a business call and say, okay, the month before, 2 months before we do the product launch, we will build twice as much of product lines B and C, and then product lines B and C will be used, their testers will be used to help test and get the big bubble of product out on top of the new product launch. So for risk reduction, this is an over time thing. So initially, if you go with a test platform approach, if you're not careful, the risk is higher than doing an individual test station. But once your test platform starts to mature, then the risk goes down dramatically. And this is because you have a body of evidence. You've got a body of work that says, okay, if I wanted to do a new test station variant and I need to test something, I've got all this pre-done work that has been validated, it's been tested, I know it hasn't gone stale because you use it in the factory on a daily basis. And we can just take the pieces and pick them up and pull something out pretty quickly. So there's a lot less unknowns at that point in time. At a certain point, it becomes stupidly easy and basically becomes a turnkey operation. Most corporations make similar types of products. And once you've got the formula down for what is needed to test that type of product, then putting together a test station based on top of your test platform gets pretty easy. So the killer feature on top of test platforms too that gets people tripped up is the marginal cost of test development. And this is where you have the most divergence between test systems and test platforms. And this is where you end up in the design by committee trap, and where you end up, if you're not real careful with how you handle this part of the development, this is what will kill your automated test platform. And basically it boils down to how much does it cost to test a new product. So how much does it cost to add a test? How much does it cost to change a test? And the answer to these questions is a balancing act. If you try and make the test platform too generic, then you end up with a Swiss Army knife or a jack of all trades, master of none type situation. If you do go too far the other direction towards a test system, you end up with something that's very optimized for a specific set of circumstances, and outside of that, it's completely useless. With the switch matrix, you can pretty easily change the route the pins on the interface connector to the instruments, and that gives you a lot more flexibility, but you still need to be careful with it. I've seen issues where it doesn't make sense. It makes sense to make the test platform, but you may make a test system out of your test platform components. So it may have a connector on there that connects to specific instrument without the switch matrix for cost and schedule reasons, but you're still using your standardized libraries, you're still using your standardized instruments, and you're taking that type of methodology. There is business decisions where it doesn't make sense to put a switch matrix and an IT on there. I've seen instances where people got more overly complicated than they probably needed to, and then you end up with a situation of, if it costs you $25,000-$30,000 to build an ITA to connect to your test system, then I would just spend the $20,000-$30,000 and build another test system. So it is a balancing act. It depends on how you connect your ITAs and what your domain is. Some of them are easier than others. For instance, if you're doing like a set-top box and you've got Ethernet and you've got power in and stuff, it is a lot of times cost efficient to have a ATE that has just the standard cables coming out of it that go to a switch matrix or don't, depending on things like Ethernet. You probably don't want to put on a switch matrix, and then you have an operator hook it up manually like that, or hook it to some sort of fixture. But if you do it that way, then you have a lot of flexibility on how you can hook up to the tester, versus if you just have a pin filled, then you have a lot more flexibility in how you can build the fixtures, but a lot less flexibility in how you hook a unit up to it. So the advantage of this is that you will typically end up with, for a specific set of products, a set of standard interfaces that make life a lot easier once you understand what that is. So one of the things that I would recommend is if you're going to do a custom interface panel for your system, then use a DB series connector, so a DB25 or DB62 or something on there. The advantage of that is it's cheap to get all the cables to make to it, and then you can make an interface cable from whatever you've got to a DB connector to hook up into the station. And then your cost of testing a new product is, the hardware cost is very little. It's just wire and pins and connectors. But then you end up getting ahead because you don't have to field an entire tester when you get a new device. So it's a little bit hard to explain. It's kind of a complicated situation on top of that. But one of the things if you have it set up correctly, then the marginal cost of adding another product to one of your ATEs should be close to zero. And that sounds pretty extreme, but I'm serious on that too, because if you've already got a standard set of instruments on there, you've got a switch matrix, you've got a standard set of tests for a given product line. So for instance, if you're doing like some sort of piezoelectric ceramic and you have a standard set of tests to test capacitance and resistance and stuff like that on top of that component, then interfacing to the tester should be fairly easy. And then you can fork an existing design, make a copy of it, change the parameters to your existing product, and then away you go, versus having to start from scratch every time you come up with a new product. So that is the basic